The modern consumer views fire simply as a crude method of producing localized heat, relying on massive, vulnerable utility grids to deliver winter electricity at astronomical premiums. Meanwhile, highly self-sufficient off-grid communities have recognized that a standard wood stove is actually a massive, untapped thermal reactor capable of generating raw, continuous electrical current. No turbines, no moving parts. Just a semiconductor wedged between hot iron and freezing air, extracting energy through a physics principle most people have never heard of. A wood stove's surface is not just hot iron. It is a live voltage source waiting to be tapped. The physics is ruthless in its simplicity. Take bismuth telluride, the backbone of every serious thermoelectric module. Its Seebeck coefficient S mod clocks in near 200 microvolts per Kelvin. Lay down a temperature gradient, for example 150 degrees Celsius between stoveplate and winter air, and the open circuit voltage is set. The open circuit voltage equals the Seebeck coefficient times the temperature difference. That is 0.2 millivolts per degree, multiplied across a 150 degree gap, delivering 30 millivolts per leg pair. With 127 pairs in a standard module, the total open circuit voltage lands at roughly 2.5 volts. But voltage alone is a half-truth. Every module has an internal resistance Rint of about 2 ohms for a 40 by 40 millimeter plate. Maximum power is not a guess, it is a formula. Pmax equals V OC squared divided by 4 times R in teat. Plug in the numbers. A 2.5 volt open circuit module squared over 8 ohms yields just under 0.8 watts at the thermal peak. Real-world modules sourced for $20 to $40 each consistently match these figures when tested against datasheet values. This is not theoretical. With 6 modules in series, a stove can drive a 12-volt load at 0.8 amps, pushing nearly 10 watts into a battery bank. The source resistor circuit is brutally honest. The only losses are internal resistance and thermal leaks. No gears, no inverters, no spinning magnets. Just a direct conversion of fire into current, dictated by the Seebeck law and the cold logic of Ohm's law. The numbers do not lie. Thermal energy forced through a bismuth telluride stack is voltage and power by design, not by chance. Heat doesn't care about market rates or grid failures. It moves by the laws of conduction through every layer between the firebox and the cold side of a thermoelectric module. The entire extraction system is a thermal resistance network. Each layer from cast iron to copper spreader, graphite pad, bismuth telluride legs, ceramic substrate, and finally the cold side heat sink acts as a resistor to heat flow. The governing equation is Q-cond equals delta T divided by R thermal. Here, Q-condy is the rate of heat conduction in watts, delta T is the temperature difference across the stack, and R thermal is the total thermal resistance, measured in Kelvin per watt. Every watt of electrical output is chained to this flow. Too much resistance anywhere in the stack and the module suffocates, starved for temperature gradient. Too little resistance, and the fragile semiconductor legs overheat and fracture. A standard 40 by 40 millimeter bismuth telluride module typically lists R thermal as a variable. Manufacturers withhold the hard number, but datasheets confirm its presence. Each interface adds to R thermal. A rough stove plate, a poorly torqued bolt, or a cheap thermal pad all become bottlenecks. The stack is only as good as its weakest layer. For a stove surface held at 300 degrees Celsius and a cold side at 30 degrees Celsius, the total delta T is 270 Kelvin. If the combined R thermal is, for example, 1.4 Kelvin per watt, the heat flow through the module is 193 watts. That is the Q-cond forced through the legs. Regardless of how much is converted to electricity, most becomes waste heat. but every watt of output depends on this relentless mechanical push from hot to cold. This is not about paying for power, it's about mastering the thermal path. The engineer's checklist starts here. Measure the stove's hot face, tally every layer, calculate total R thermal, and ensure the module's delta T is real, not just a guess. The physics is unforgiving. If the thermal bottleneck isn't controlled, output collapses. If it's optimized, the module delivers continuous current all winter, indifferent to the sun, the price of copper, or the state of the grid. Every experiment lives or dies by the quality of its measurements. Replicating stove-based thermoelectric extraction demands a checklist that tolerates no ambiguity. Start with the core, a calibrated Type K thermocouple for each module. Hot face, fixed directly to the cast iron using a stainless spring clip. Match this with a second thermocouple on the cold side, pressed against the heat sink or cooling plate. For electrical output, use a 4-wire voltage tap across each bismuth telluride module, preferably with Kelvin connections, which eliminates spurious drops from lead resistance. Current must be logged through a shunt resistor rated for at least twice the expected peak. 1 ampere, 0.1 ohm, 1% tolerance is standard. Data logging cadence cannot be left to chance. Field best practice is 1-second intervals, exporting to a comma, separated values file with columns for time, hot side temperature in degrees Celsius, cold side temperature in degrees Celsius, voltage in volts, and current in amperes. Each module gets its own row. Use a battery-backed logger or microcontroller with non-volatile memory. SD cards alone are not robust enough for multi-day tests in a stove room. For multi-module arrays, assign a unique identifier to each sensor pair. Never trust handwritten notes. All readings must be time-synced to within 1 second, or cross-module comparisons become meaningless. The minimum test gear is 2 Type K thermocouples per module, 1 4-wire voltage tap, 1 shunt resistor, a data logger capable of 1 Hz sampling, and a comma-separated values export function. Optional items include a clamp meter for spot checks, an infrared thermometer for surface scans, and a backup USB power bank for logger uptime. If the dataset lacks any of these, temperatures, voltages, currents, or timestamps, it is not replicable. The protocol is mechanical and absolute. Measure, log, export, verify. Only then does the experiment move from theory to actionable engineering. Mounting a thermoelectric module to a cast iron stove is not a matter of guesswork. It is a mechanical gauntlet. The surface temperature at the firebox crown can spike to 316 degrees Celsius during a hard burn, but bismuth telluride modules are only rated for a hot side maximum of 250 degrees Celsius. Direct contact is a death sentence for the semiconductor. The solution is a layered interface, a 1 mm copper spreader plate bonded to the stove with high temperature silicone, which levels out the thermal spikes. This spreader absorbs local surges, distributing heat laterally, so the module never sees a flashover above its rating. Between the copper and the module sits a 0.1 mm graphite-based thermal pad, high in conductivity, about 5 watts per meter Kelvin, and compliant enough to fill every micropit in the cast iron. The pad must be pre-cured at 200 degrees Celsius to drive out any volatiles before it faces firebox duty. Clamping pressure is critical. M4 stainless steel bolts, torqued to exactly 2.5 Newton meters, deliver a uniform 0.5 megapascals across the ceramic module face. Too loose in the pad gaps, spiking thermal resistance. Too tight and the brittle legs shatter. A torque wrench is not optional. Every 6 months, the bolts must be retorqued to account for the thermal expansion mismatch. Cast iron expands at 10 × 10 to the -6 per Kelvin, while the module ceramic legs move at only 3 times 10 to the -6 per Kelvin. Neglect this, and shear stress will crack the interface. No combustibles may come within 25 millimeters of the assembly, per NFPA 211 and ANSIZ 21.11.1. All wiring must exit the cold side, routed through a heat-shielded junction box, rated for 150 degrees Celsius. The module stack itself is shielded with a 300 degrees Celsius silicone gasket, and an optional stainless cap blocks creosote and soot. The mounting bracket never pierces the firebox. No protruding fasteners, no shortcuts. If the copper spreader and pad are installed to spec, the module survives years of thermal cycling, delivering continuous current even as the grid outside flickers and fails. This is not a luxury retrofit. It is a hard mechanical necessity for extracting power from fire in the heart of winter. Solar panels collapse under winter's iron sky. At 45 degrees north, daily insolation falls from 5.5 to barely 2 kilowatt hours per square meter. That is a 64% drop in raw sunlight. Photovoltaic output nosedives, down 40 to 70% in December, even before snow and ice finish the job. The numbers are brutal. A 500-watt photovoltaic array that delivers 2 kilowatt hours in June will struggle to produce 0.8 kilowatt hours in deep winter. Short days, low sun angle, and constant cloud cover combine to strangle output, right when demand peaks. Meanwhile, a burning wood stove becomes a relentless thermal engine. As the outside temperature falls, the temperature differential, delta T, between the stove's hot plate and the freezing air only grows steeper. The Seebeck effect rewards this gap. Every degree of extra chill on the cold side multiplies voltage and power. At -10 degrees Celsius, a cast iron stove running 300 degrees above ambient delivers a delta T of 310 Kelvin. That is not a theoretical maximum. It is the lived reality of 6-month winters on off-grid farms. Solid-state bismuth telluride modules, bolted to the stove's rear or crown, turn this hostile climate into a power advantage. Module output rises, not falls, as the mercury drops. Passive aluminum fins or water-cooled exchangers keep the cold side near zero, pushing continuous current into battery banks while solar arrays sit idle beneath snowdrifts. A $30 module under a 300-degree gradient delivers up to 0.3 watts, multiplied across arrays of 10, 20, or 30 units. The physics is mercilessly simple. The colder the winter, the bigger the payoff. In the dead of January, fire becomes a 24-hour generator, immune to grid failures and the false promise of winter sun. The payoff is mechanical, not financial. In these latitudes, only thermal extraction holds the line against the darkness. A wood stove, stripped to its bill of materials, is a ledger of thermal opportunity. The cost of entry for solid-state fire extraction is not a secret. It is a sum, line by line, in dollars and watts. The core is bismuth telluride modules, typically 40 by 40 millimeters, sourced direct from Alibaba. At scale, a single module runs $18 to $25, bulk pricing for quantities of 10 or more. For a 12-volt battery bank, the minimum functional array is 6 modules in series, $120 to $150, just for the semiconductors. Add a 1mm copper spreader plate for each position, $12 per sheet, and graphite thermal pads at $6 apiece. Stainless M4 bolts and washers, $2 per module. Passive aluminum heat sinks, $18 each, 6 units required. Total for the thermal stack, $270. The wiring is not optional. High temperature silicone leads, $15 for a 10-meter spool rated to 200 degrees Celsius. A heat shielded junction box, $25. UL listed for 150 degrees. The charge controller, a DC to DC boost module like LTC3108 or BQ2557 comes in at $40 for a reliable MPPT capable unit. Add a battery-backed data logger for $60 and a set of calibrated Type K thermocouples, $35 for a 6-pack. The subtotal for control and monitoring, $175. Mounting hardware and safety compliance are not afterthoughts. Stainless brackets, $30 for a set of 6. High-temperature silicone gasket, $14 per tube, 1 tube per stove. Optional stainless cap for creosote protection, $28. The mechanical envelope clears at $72. Fire code compliance, NFPA 211 and ANSIZ 21.11.1, demands a non-combustible backplate and a 25mm air gap, adding another $40 for mineral wool and steel shims. Tally the numbers. Modules and thermal stack, $270. Control and monitoring, $175. Mounting and compliance, $72. Safety and code, $40. The real bill of materials, with every required part, lands just under $560. Add contingency, shipping, spare modules, thermal paste, and wire loss, $140. The all-in cost for a robust, code-compliant, winter-ready thermoelectric extraction system is $700, not a penny less. This is not a toy. For $700, the array delivers 10 to 12 watts continuous at a 250-degree gradient, enough to charge a deep cycle 12-volt battery bank, run LED lighting, and power a radio or water pump through the longest winter blackout. Amortized over a 10-year module life, the capital cost per kilowatt hour is brutal in its transparency. 7 cents per kilowatt hour, assuming 1,200 hours of stove operation per year and 12 watts output. The math is mechanical, not speculative. Wood is the only ongoing fuel cost. No grid bill, no solar panel replacement, no inverter failures. The price per watt is not a guess. Each module, each bolt, each thermal pad is a line item, a physical commitment to energy independence. The grid outside is a liability, volatile rates, rolling blackouts, fragile PV arrays buried under snow. Inside, the stove burns and the modules work, indifferent to the weather, the market, or the sun. Fire is the original off-grid currency, and in this ledger, every dollar buys not just heat, but uninterruptible winter power. Series wiring is not a suggestion. It is the only route to real voltage. Each bismuth telluride module delivers a meager 2 volts open circuit under a hard winter gradient. To crack 12 volts for deep cycle battery charging, 6 modules must be chained in series, each one a high impedance node in a brittle electrical ladder. The resistance stacks mercilessly. 6 modules at 8 ohms each yield a 48 ohm array. The current, at best, is 0.33 amps when the stove's hot plate holds at 300 degrees Celsius, and the cold side sits just above freezing. That is 4 watts raw before the boost converter takes its cut. Parallel wiring, often touted in do-it-yourself forums, is a dead end for voltage. Stringing modules side by side piles up current, but leaves voltage stranded below the battery's threshold. Only a DC to DC boost converter, like LTC3108 or BQ25570, can step up a single module's output, but efficiency nosedives below 1 watt input. In practice, arrays are built in series to guarantee voltage, then paralleled if more current is needed. Each string must be temperature matched. A single cold module drags the whole array down. Daisy chaining across uneven stove surfaces is an invitation to imbalance and early failure. The data logger delivers the verdict. A 48-hour CSV export, sampled every second, lays bare the numbers. 6 series wired modules. Cold side at 5 degrees Celsius. Hot side at 295 degrees Celsius. Output 0.33 amps at 12 volts. That is 4 watts, steady, through the night. Charging a 40 amp hour battery at this rate takes more than 150 hours, 6 days of continuous burn. The BioLite camp stove curve, often cited in manufacturer literature, confirms the limit. 3 watts peak from a single module under ideal lab conditions, with real-world output closer to 2.4 watts during field cooking cycles. No module, no matter the brand, escapes the Seebeck law or the tyranny of internal resistance. Efficiency curves from the LTC3108 and BQ25570 datasheets are blunt. At 0.5 watts input, post-conversion efficiency hovers around 60%. Push above 2 watts, and it climbs to 73%. The cold numbers do not lie. 1 watt in, 0.6 watts out. 10 modules in series, each at 0.4 watts, yield a net 2.4 watts delivered to the battery, enough for LED lights, a radio, or a water pump, but not a mirage of fast charging. The physics is ruthless, the economics transparent. At $30 per module, a 10-unit array costs $300. Over a year, the system delivers about 52 kilowatt hours, $7.80 of avoided grid cost at current rates. The real cost per kilowatt hour, factoring module, depreciation, and wood fuel, lands between 4 cents and 7 cents. The 48-hour log exposes every claim. The current never spikes. The voltage never surges. The array's output is mechanical, continuous, and brutally honest. There is no hidden surplus, no free lunch from fire. Yet in the dead of winter, when solar collapses beneath snow and the grid flickers, this trickle of power is relentless, always on, always local. The stove burns, the modules work, and the numbers are final. Energy independence. Here is not a slogan. It is a CSV file, time-stamped and verified, running through the darkest nights without apology. Right now, every kilowatt on the grid is hostage to outages, fuel prices, and failing infrastructure. A $20 bismuth telluride module, welded to cast iron, ignores the sun, the wind, or grid collapse, delivering 24-hour voltage from a pure thermal gradient. In winter's blackout, the Seebeck effect is not theory. It is survival. Thermoelectric fire turns scarcity into autonomy, one closed circuit at a time. What matters is what you build next.